Okay, so our final fluids lecture, which will be much quicker than any of the other ones that we have done before. So we're going to talk about Torricelli's theorem. We'll do a really cool lab with Torricelli's theorem, which is why I bought those tubes, and you'll see why. So I can derive Torricelli's theorem, and I can solve problems using Torricelli's theorem. So once again, all about Torricelli's theorem. Okay. So we can use Bernoulli's principle to find the speed of a fluid coming out of the spigot of an open tank, and the result is called Torricelli's theorem. So if we look at our diagram here, if we look at both points 1 and 2, they both have the same atmospheric pressure because they're both exposed to air. So if we take that into consideration, we could say, okay, well then P1 is equal to P2, which is just equal to the pressure of the atmosphere. Okay. And we can also make the assumption that if we're at the top of the fluid here, the speed of the liquid lowering at that point is extremely slow, so we could say that V1 is equal to 0. Okay, so if we continue to derive Torricelli's theorem with those things in mind, we can say, okay, let's look at Bernoulli's principle and continue to reduce for Torricelli's theorem. So we say, okay, P1 plus rho g y1, and y1 and y2 were defined in the previous slide. Rho v1 squared, which is equal to p2, plus rho g y2 plus 1/2 rho v2 squared. Now, once again, things are going to cancel. We said that at the 2 points you had P1 and P2 are equal to each other because they're both exposed to the atmosphere. And then you have V1 is equal to 0 because the velocity of the water at the top as the water is being pushed out of the spigot is extremely slow, to the point that you can set V1 equal to 0. So we're left here then with rho g y1 is equal to rho g y2 plus 1/2 rho v2 squared. Now, of course, once again, we are assuming an incompressible fluid, so density is going to be the same. So we're left with gy1 equals gy2 plus 1/2 v squared. And we're trying to solve for the velocity, squared. My pen is acting up. We're solving for the velocity at which the fluid, in this case the water, is going to be leaving the container at that point. So we could say, okay, V2 is then equal to the square root of 2g times y1 minus y2. Okay, and this is what is called Torricelli's theorem. Okay, so we're solving for the velocity with which the liquid leaves the container horizontally at some point 2, and that velocity is the same as if an object would have dropped from some height y1 minus y2. Okay. So some examples and then we will be done. Once again, this is a really quick one, which is nice. Okay. So example 1, a container of water has a spigot at its bottom. What happens to the water speed out of the spigot as the container empties? So hopefully it makes sense that the speed of the water should decrease. Okay. So as it empties, we know that velocity is proportional to, or is equal to, this, right? By definition of Torricelli's theorem. So if this is getting smaller as the water level is obviously going down, then that means that the water speed is also going to decrease. Okay. A container holds water at a depth of 5 meters. There's a hole in the bottom of the container, and we want to figure out with what speed the water is going to flow out of the hole. So this one's pretty straightforward. This one's just actually plugging in numbers into Torricelli's theorem. and we're saying, okay, the water is at a depth of 5 meters. That means that you can call y2 0. Just call that the ground. It makes it easier. And that will, when you calculate that out, that's 9.9. So water tower A is filled with a certain depth of water. Water tower B is filled with 4 times that depth of water. If both towers are the same height off of the ground, how much farther away will the water from B in the tower land? So I know that V is proportional to the square root of depth, right? The 2g doesn't really matter in this case. So that means that V squared is going to be proportional to delta x. So if we're saying, okay, the depth is 4 times greater, that means that it's going to go twice as far because you would just take a square root, and hopefully that makes sense. Like I said, we'll do a really cool lab with this. We will make an absolute disaster of my classroom with all the water, I am sure, but it'll be fun and interesting, and that's a good enough reason to do it for me. So you are now done with notes for this unit, so no more notes until thermodynamics unit, which starts at the end of September.